Welcome. Thanks. So our company does make optical chiplets and optical engines for co-packaging, but I work a lot in the standards area, especially with the OIF. And we have a project there called Energy Efficient Links for the data centers, and it's really driven by the need for AI/ML. So what I thought I'd do today is talk a little bit about the concerns and the issues that the hyperscalers are driving us towards. So this first chart, you've all seen this kind of stuff before, but I think the key takeaways are what's in yellow. What these trends...
It's not synced right.
Okay.
Do you know where the problem is? Is it at our end or your end? The screen isn't... Do you click the button? There you go.
Okay. Okay. So anyway, here's the... these charts you've seen before, but I think the key thing is the takeaways here, they're in yellow. What these trends are doing is pushing us towards reduced power consumption, improved density, and reduced latency. And you'll see that as we go through this. I thought it would be worthwhile to talk about the applications in the data center. This is a chart that was contributed to the OIF. I've modified it a bit from Microsoft, and it shows the back-end and front-end parts of the network. And in particular, the AI/ML is really driven by the part that's in green. And in particular, the PCIe stuff is the part that's got the background yellow area in it that has, computer to I/O, compute to memory, and compute to compute. And we've listed there the different kinds of protocols that people are using. And what I wanted to highlight here is some of the key characteristics for these kinds of links, which are, they can be bookended, or they can be standards-based. They're definitely low latency, energy efficient, and potentially high density for some of these applications. So what we do now is step back and look at what are some of the architectures, things you could do to achieve some of these objectives. So in this chart at the top, I have columns here with the objectives: latency, density, energy efficiency. I've also added one called link accountability, which is becoming very important. Link accountability basically means if you assemble this link, how do you know it's going to work? And if it doesn't work, how can you figure out what actually is wrong with it? So the classical way to do this is using retimers, and so the top level shows that. But you can save power if you get rid of the DSP, but then you can see that the link accountability kind of goes away. You can do this co-packaging, in which case you get nice, short, consistent electrical channels, and you can get a lot of green things. I'm not trying to say which of these approaches is the best. I'm just pointing them differences, and depending on the particular application, one of those might be better than another. So now if we then take a look at particular PCIe and doing these energy efficient links, there's really two major bottlenecks. One is the impact of meeting PCIe compliance, and the other are the pain points for the PCI protocol. So let's dig into those a little bit. So in terms of PCI compliance, I'm showing here a root complex and an endpoint, and in between is a copper cable, and in red I've delineated where the PCI compliance points are. So that's what people do today. Those are the standard PCI link. Now in this second picture, what I'm doing is I'm showing an optical link that's embedded in this PCI link. But what I'm using in green boxes there, it's what's called an optical enabled PCI retimer. So this is a PCI retimer that has optics with it, and then you have an optical link. Now the good thing about this is the PCI compliance points are well defined. You can see at the root complex to the first retimer, there's, you have those red compliance points, and the same on the right side. And there's a potential to do optical, to come up with some optical standard for compliance points for the blue optical link, but that's today that's not something that's being defined. Now on the bottom, to get better energy efficiency, you could try to remove the retimer out of the link, and so now you have what I would call a non-retimed or maybe a partially retimed transceiver in there. But now what happens is the PCI compliance points go back to the endpoint and the root complex. And so this is a conundrum in terms of standards, is how do you define this and make sure it's interoperable across a number of suppliers. So now let's dig into this a little bit more. So in this case where we're using these optically enabled retimers, this optical link could be bookended. For instance, it could be an active optical cable, Or it could be, like pluggable transceivers with some kind of optical link standard between them. Like in Ethernet, there's DR4 and FR4 kinds of things. If you go to a link without a retimer in it, what happens is if there's a signal quality issue at one of the ends, say the left end where there's a copper cable link, though that signal quality bleeds over into the optical link and then shows up at the other end. So you kind of get this mixture. It's hard to come up with good compliance points between the other, and this is one of the key challenges that we're looking at in the standards groups, how to develop a methodology for that. One of the things you notice when you get rid of those retimers is now, if you want to really make this truly interoperable across a number of technologies, you end up sacrificing link budget. You just can't have it all. You can't save power by getting rid of a retimer, which actually is doing something useful, and then make it work, for everybody. The second area was about the PCIe protocol. So optics, gets used with Ethernet, and that works well. But if you look at PCIe, it doesn't. And why is that? Because PCIe was architected for a copper link. It assumes there's copper between 2 points. So what are some of the challenges in the PCIe protocol that make this difficult? So the first one here I bring up is what's called RX detection. This is where the PCIe electrical transmitter uses impedance to determine if there's a remote electrical receiver at the other end. And if there is, then it thinks it's ready for traffic and it'll try to bring up the link. But if you put optics in there, there's no way to measure the impedance at the far end. So that's something that would need to be dealt with. Another one, there's a zillion of these things, and what I've done is I've just lumped these into big categories. So the second big category is inconsistent signaling. So I'll just give you one example. Here is, in PCIe, there's a concept of electrical idle. The transmitter basically has zero differential voltage at its output. Optical links obviously are going to be AC coupled. And so the thing is that when the electrical transmitter puts out a zero differential voltage, the question is, what is the receiver going to see? If you have these non-retimed optics in between, then you kind of have a large amplification chain. And the question is you're close to a couple of millivolts at the transmitter, how many millivolts do you have at the receiver, and do you meet the compliance specs? Another one is that when you're in electrical and you're coming out of it, you start transmitting a data signal, and now what has to happen is the receiver at the other end has to start lock in on that, get to a good consistent bit error rate, and start, receiving traffic. The problem is that the time for an optical link to stabilize and start transmitting low bit error rate is probably longer than the timeout of the electrical receiver in the endpoint. So that's another area. There's several other considerations bring up. So one of them is there are some signaling states that are very close to the low cutoff frequency of optics. There's also accommodations might need to be made for sideband signals, which are used today in PCIe links. And there's also the concept of different kinds of clocks in PCIe. And so one of them is spectrum clocks, and that's a naughty thing to use with optics. So there is a mode called SRNS, separate reference clock, no spread spectrum, which would be a good choice for that. So in summary, if you have a non-retimed PCIe link, you're probably going to need some adaptations to the protocol to actually make this work well, especially across a multi-vendor area. And if you use an optical-enabled retimer, at least you can compartmentalize that so that the root complex and endpoint actually don't need to know there's optics in the middle. The retimers, optical-enabled retimers in the middle link can basically hide the fact that there's optics there, and then it becomes interoperable across many implementations. So in standards, one of the things that's really important then is how do we come across and develop optical standards. So many suppliers provide optical models for their products, but these are often proprietary. They're maybe on different platforms, or often computationally intensive, and but they're important. So one of the steps forward is to come up with a generic technology independent model. And that's something that we've been looking at the OIF. So this allows us to basically provide a set of coefficients, and it can model a variety of different optical links, and this can be used as we develop standards. So in summary, I think as we talked about, the key drivers are reduced power consumption, reduced latency, and improved density. And as you saw from the presentation in the last session, if you saw it, was from Meta, and I think if you saw some of the ones from Microsoft and others here, building this ecosystem and getting to these high yields and high volumes and being able to scale, that's really important. So I think that's where standards come in, interoperability between various vendors as well. So as we saw, there's a variety of architectural approaches to achieve these objectives. And one of them could be an optical enabled PCIe retimer or redriver. Another one is to use these non-PCIe retimed optical links. Each has their pros and their cons. And then there are several challenges with achieving these objectives that need to be worked on. So one is how we're going to specify compliance, especially when there aren't retimers in the link. And then also choosing a strategy to address the PCI protocol, which is really not completely optics friendly. How can we adapt that, or could we hide it with a PCI optical enabled retimer? So I think I hope that was interesting too. It kind of gives a view from a standards point about how to move the industry forward, so we can really scale and make these things a reality. Thanks.
Questions? Is there any activity in the PCI standard to make it optics friendly?
Yeah, so there's an optical cabling work group, and there's also an optical sub-team track that's been started that's working on that. The optical cabling group is going to work on making the PCI protocol more optics friendly.
Good. Okay. Okay, let's thank the speaker.